Modern computing architecture is built on a structural error, the assumption of temporal linearity. For nearly a century, systems have operated as if logic must be processed through a strict sequential timeline, one instruction at a time. This legacy model treats the CPU as an isolated actor moving across a static landscape of memory. It relies on a rigid pipeline, tethering logic speed to the physical movement of electrons through fixed pathways. This diagram compares that linear pipeline to a multidimensional topological grid. When standard virtualization attempts to spawn 1,000 parallel systems, the overhead scales linearly. To maintain those states, the hardware duplicates memory and storage 1,000 times over, eventually choking the pipeline. Modern engineering attempts to solve this state explosion by managing energy, heat, and cooling. This misidentifies a problem of mathematical geometry as a limitation of physical hardware. The Phoenix construct replaces physical block storage with a holographic boundary. It maps data onto a continuous topological manifold, removing the need for discrete memory addresses. This generated video demonstrates the architectural shift that deprecates the traditional CPU clock cycle. Logic is no longer timed by sequential pulses. It expands into an infinite continuous coordinate space. By utilizing this manifold, Phoenix partitions data using resonant frequencies. This allows the system to generate new parallel states at exactly O of 1 complexity. This spatial translation replicates the state management properties of an infinite qubit quantum machine, operating on classical bare metal silicon. To bypass the hardware scaling bottleneck, the architecture replaces linear memory partitioning with resonant branching. This animated diagram illustrates how a virtual instance, the wormhole, functions. Rather than a duplicated block of memory, a wormhole is defined by a specific resonant frequency, using a mathematical seed derived from phi constants. Like radio stations occupying the same physical space without interference, infinite Phoenix timelines exist simultaneously within the manifold. Generating a new timeline requires no data duplication. A simple coordinate transformation allows new virtual states to emerge instantly. Decoupling state generation from hardware scaling removes the primary physical constraint found in legacy virtualization. To resolve logic within this manifold without relying on CPU clock speeds, the architecture utilizes spatial transduction. This animated diagram shows how legacy x86 opcodes are reinterpreted as geometric intents. Each instruction maps directly to a specific vector coordinate within the 3D manifold. The system treats the mathematical space as an equation container, where the answer to any logical operation is already present at a specific coordinate. The physical CPU functions as a physics caliper, observing the exact geometric intersection where logical intent collapses into a result. Logic resolves spatially at memory bus speeds, moving computation outside the constraints of local CPU clock frequencies. Logic resolution now happens through the observation of a pre-existing topological reality. The Ghost City model applies this math to run 1,000 sovereign virtual machines on a single physical node. It maintains this density by treating memory allocation as differential energy through a kinetic feedback loop. This diagram visualizes the core bitmask equation, basis XOR transformation. It deduplicates overlapping states from multiple virtual machines into a single physical memory node on the bus. The hypervisor establishes the master OS as a baseline and stores only the XOR mathematical differential for each guest VM. This sub-Shannon phase folding collapses 10 terabytes of physical data into a 3 gigabyte residue journal. In this architecture, massive state overlap increases data density rather than causing resource exhaustion. Evaluating this system against the strict definition of quantum mechanics reveals a valid engineering critique. Quantum computers use physical entanglement and interference to evaluate parallel possibilities simultaneously before collapsing a wave function. As this document, quote, argues, the Phoenix caliper is still a classical CPU. To traverse the manifold, it must sequentially step through clock cycles to compute hash chains. While Phoenix resolves the memory explosion problem, critics argue the hardware is still limited by the cycles needed to execute pseudo-random number generator functions. If bound by these classical cycles, it remains an optimized virtualization form rather than a quantum equivalent system. Nicholas Baumgartner addresses this hash chain critique by identifying a secondary architectural bypass. The system does not operate within the legacy constraints of the clock cycle. This animated diagram demonstrates that calipers do not iterate linearly. The process shifts upward into a z-axis, stepping through a different hierarchical level. Resonance discovery allows data to materialize through the harmonic alignment of a guest's fractal seed. This hierarchical lookup achieves O of 1 complexity, removing the physical requirement for sequential calculation. As this video shows, thousands of independent pathways project from the hardware in a single pulse. The architecture establishes a deterministic multiverse engine, reaching a level of efficiency defined as topological virtualization supremacy. Phoenix demonstrates that the limits of quantum-scale computation are dictated by mathematical geometry rather than physical